Good afternoon, everyone, and thank you for attending our Electric Snow Melting Systems webinar. My name is Ryan Wood, Content Marketing Manager here at Liberty Electric Products. Before we get started, I just want to let you know that you'll all be muted during the presentation, and we will not be doing a live Q&A. If you have any questions as we move along, please enter them into the questions panel, which is located in the webinar control panel, and we'll be sure to reply back to you by email. Also, we will be recording this webinar and we'll post both the recording and the slide deck on our website and YouTube channel. Our presenter today is Rob Zerillo. Rob has been in the industrial commercial heating business for over 16 years. First working with the Cleveland Brooks distributor, and then for the last 12 years with Liberty Electric Products with a focus on electric heating applications. Rob has worked on and developed solutions for more than 500 different heat trace applications in upstate New York. His primary responsibility is being in the field at job sites, working with engineers and architects on new designs, and helping contractors with installations. So without further ado, I'll pass it over to Rob.
Thank you, Ryan. And thank you, everyone, for spending some time with us this afternoon. We really appreciate it, and hope you get some great information out of this content. To talk just a little bit more about just the agency, I've been with Liberty Electric now, as Ryan was saying, for a little over 12, 13 years now, and we've grown by leaps and bounds. We have been at it since 1987 here, and predominantly had our roots in electric heating applications, which is something our customer base is known and has relied on our expertise for years. Our brick and mortar location is in Syracuse, New York, and over the past 8-9 years, we've been in acquisition mode. We've been growing by acquiring other rep agencies, increasing our line count and our outside and inside support staff. So if you've worked with us in the past, we've got an excellent reputation for servicing our customers, trying to get answers back to folks on time with high technical accuracy as well. And as Ryan had mentioned, a lot of my time is spent typically with specifiers, also calling on both electrical and mechanical contractors, helping them to integrate these products, install them correctly, understand more about them, and of course, being a liaison to end user accounts as well. And enough about me. Tricia Newberger is really who helps orchestrate a lot of what goes on here at Liberty Electric. She's our operations manager and oversees the inside group, and does a fantastic job of getting traffic to where it needs to go, let's say, in terms of slotting people towards our different product and manufacturer experts. Ed Jordan is really the guy when you're looking for some design and technical help. He's our inside heat trace engineer that does all of our design work and quotations, and I'm the outside side of that equation that typically I go out and look at job sites and relay that information back to Ed. But ultimately, if you need any answers or some quick service regarding any of the products and applications that we're going to learn about today, Ed is a great resource that you can get a hold of probably faster than you can get a hold of me, as I'm usually on the road for 4 days a week. So without further ado, let's take a look at our agenda for today. We're going to talk a little bit more about the different types of heating elements. I think it's good to have a foundation of understanding what kind of products we would typically use in these applications. So as you can see here, we've got 5 different products or so we're going to review briefly, and then get into the applications themselves. We're going to talk about roof and gutter de-icing and its associated controls, and then sidewalk and pavement de-icing. And you'll see that there's a lot of similarity between the controls on both of these applications. And then we're going to finish it up with a little, just a few pointers on like installation and best practices. All right, so let's get into snow melting elements. So as you can imagine, basically there are different types of snow melting elements, and really they vary in what they're used for. Most of the controls are very similar, and we're going to hit on that in future slides here. But one of the things to keep in mind is, as with most engineered product, is the higher quality manufacturers, I guess what I'm trying to say is you get what you pay for. Okay, there's definitely differences in life expectancies of these products, and some products are made more inexpensively than others. So, I can at least attest to the point that generally your more expensive products, more expensive brands are going to be much more commercial, industrial driven and have a life expectancy that say matches that. If you're looking to buy on price, again, you kind of get what you pay for there. So, another big difference, and again, I'll reference back, you folks might get sick of it by the time I'm done with this presentation, but between my mechanical days when I helped design hydronic snow melting systems versus where I am on the electric side of the fence now, I'm always doing comparisons between these two. And one of the things that I really liked about the electric side of this application is that electric elements can generally be repaired, pretty easily. It's more of an issue of finding them if there's an issue, which again, I think that a lot of times that can be the same, no matter what you're using for the application itself. One of the things we're going to talk about, or the first element I should say we're going to talk about is the most popular, which is the self-regulating cables. Certainly for roof and gutter de-icing applications, the self-reg cable is really, the majority of this application. And one of the things that really makes this a very, very popular cable is the fact that it's the only one that you can touch it against itself without fear of it burning through. Okay, but we're going to talk a little bit about how this product gets its name and how to figure it out a little bit better. Okay, so the industry standard for self-regulating cable, when we talk about having a wattage value per foot, or how much heat this cable puts out per foot, the industry holds to a 50-degree standard temperature as its rating. And a self-regulating cable works off of expansion and contraction. Okay, the entire magic to how this cable works is based off the surface temperature of what we have it up against. So just real quickly, when you warm things up, when you put them against a warm surface, most materials want to expand when you heat them up. So the inner core of this cable actually expands when you heat it up, and it pushes the bus wires a little further away from each other, which reduces wattage output. And conversely, when you make this cable very cold, if you put it against, say, a surface like a block of ice, as things do when they get very cold and want to freeze, they constrict, they pull in. And as this cable tightens up, it opens up more electroconductive pathways in that irradiated carbon, and thus heats the cable up. So you've kind of got a throttling effect that takes hold across this cable on any given length. And the irradiated carbon content, I mean, just to make a quick note on, again, when we talk about price and quality, your better manufacturers have generally got pure content of carbon mastic, and their product will last longer. This is a product that does have a life expectancy, but typically, for a good commercial grade cable, you're probably looking at a 15 to 20 year life expectancy on it. So if we look at a cross section of the cable itself, you can see we've got two parallel bus wires, typically stranded wires, almost always. And then that irradiated carbon matrix there looks a little bit like black licorice, okay? And that's really where, again, the heat output of the cable is being throttled forward and back. And then you've got a primary over jacket. Now, I'm only pointing out that primary over jacket because when we talk about a cable being rated at 50 degrees F, okay, it's not going to go much below what its rated duty is because of that primary over jacket. That doesn't allow the cable to physically expand out a little further the way it would like to. So if we use, say, a 5 watt a foot cable as an example, probably the lowest output you're going to get out of a rated 5 watt a foot cable might be 3.5 to 4 watts a foot, because that primary over jacket won't allow it to expand out any further. Okay, so it's kind of important to note when you get into the designing portion of this that you're not taking that wattage output for granted, let's say. The tin copper over-braid, those were added to heat cables, probably about 5 to 10 years after they were originally incepted in the 60s. And this helps with a means for grounding. You can basically twist up that tin copper over-braid and just basically terminate that on the grounding screw, and that becomes your means of ground. And then, of course, the over jacket, depending on what the cable's function is, for roof and gutter de-icing, we usually rely on a UV inhibitive resistant over jacket. So when we talk about sizing circuits, this is also probably the most confusing part of this cable. And if you can get this, then the rest of it's pretty easy. Is a 5 watt a foot cable, let's say, for example, has a potential to draw up to 12 watts a foot at full output. So if that thing was encased in snow and ice and the system was not on automatic controls and somebody flipped a switch on, that cable is going to have a millisecond inrush current at 12 watts a foot. So we have to size our electrical circuit based off of that. So when we're doing this calculation, again, we typically use 30 amp 2-pole breakers for any of you electrical folks out there. And because we cannot exceed 80% rated duty of the breaker, again, we have to be careful as to how many feet of heat cable we can put on that circuit. Now, for folks that have had any experience with this cable before, I'm just going to point out a nice, kind of rule of thumb to this, is that when you're running power from either a supply panel to send to a junction box, and you want to come out of that junction box with heat cable along your roof or along a pipe, it's not the power run that counts footage towards your circuit maximum length. Okay, so if you had to run 100 feet of standard, pipe and wire, and you've got a number 10 inside of that conduit feeding power, you don't count that 100 foot of power wire. You're just counting feet of heat cable on the circuit before you get to your maximum circuit length. Okay. To go down a few of these bullets, though, again, the big attraction of this cable is that it can touch against itself without fear of burning through. So again, when you have two warm surfaces like this cable that touch against each other, it wants to back itself down. And the other big appealing part to self-regulating cable is that they actually get categorized also between low temp, medium temp, and there really isn't much of a high temp self-regulating cable at this point, mainly because it's a very, very niche industrial type of application. But to give you some context, a low temp self-regulating cable only works to a maximum of 150 degree output F. Okay, so it is safe to use on things like PVC pipes or asphalt shingle roofs or EPDM roofs. We don't get hot enough to where that cable is going to embed itself into the material. So that makes it an incredibly popular choice for, say, roof and gutter application because of that. So again, those are some of the reasons why you'll see self-reg cable, especially in the commercial roof and gutter segment, is probably about 99% of the product used for that particular application. And speaking about the commercial application, typically we want to be around 8 watts a foot is where we standard design for commercial application. And another reason for that is that you can also suffer voltage deration. Most heat cable manufacturers are going to design their product based around 240 volt. So when we feed it 277, let's say on the high side, instead of, say, that 8 watt a foot cable putting out 8 watts a foot at 50 F, it may actually be putting out 9 to 9.3 watts a foot, maybe even up to 9.5 at like 277 volts. So it's going to run hotter, which is a great thing when you're trying to melt snow. The only downside is that usually the higher the voltage rating of the cable, the less life expectancy it's going to have. Okay, now let me put that in perspective as well, is that if you have a better grade commercial industrial cable that's got a life expectancy of around 15 to 20 years by itself, 277 volt might turn that into about let's call it an 11 to 14 year cable, but it's going to run really well for those years that you have it. So it'll give you plenty of output. And conversely, if we look at 208 supply voltage, we're derating that cable a little bit. So again, instead of 8 watts a foot, maybe we're putting out something more like 6.7 to 7 watts a foot, which is important because one of the things that we certainly try to emphasize during the installation process or even in the design process is to take a proactive voltage reading and find out exactly what our current is getting to that cable. So again, if you've got a 208 volt facility and we're using a cable designed around 240 volt and we're expecting 8 watts a foot, we're really only going to get 7. But if that voltage is really down around 202 or 200, you're going to get even less. So these are the things that, again, we look for on the front side. So here's another slide that really depicts a bit more of what we're talking about as far as sizing the breakers. And again, this is the most complicated part about this particular cable is, being that we can't load past 80% rated duty of that breaker, When we look at an 8 watt a foot cable for this example, it actually has the ability to draw 22 watts a foot. So when we're looking to put that on a breaker, if I'm using 120 volt as my voltage, I can only go up to about 210 feet of 8 watt a foot heat cable on that circuit. And if I'm somewhere between the 208 and 277, I'm maxing out around 420 feet. So you can see it's a bit more advantageous when you're talking about trying to cover ground on a roof, let's say, where you want to use fewer circuits out of that main distribution panel that you're pulling 30 amp 2-pole breakers out of. So if we can consolidate circuits, that's a good thing. All right, constant wattage cables are exactly what they say they are. They give you a constant wattage output based on whatever its rating is. And these typically will come in, let's say 4, 5, 6, 8, 10, 12 watt a foot type cables, which is really nice as far as, you know, figuring out your maximum circuit lengths. That becomes much easier. These cables are often very flexible, easy to bend out in the field, the commercial grade stuff, and can be worked out in the field. However, the big drawback to these particular cables is that they cannot be allowed to touch against each other. There is no mechanism for these to back themselves down, and their output temperature is often far greater than that 150 F that a low temp self-regulating cable will give you. So finding a constant wattage cable rated for roof application, there isn't one that goes beyond, say, 6 watts a foot that I'm aware of in the industry. A lot of your home do-it-yourselfer kits, if you go through a big box, you know, home center store, excuse me, I'm sure you'll see some of these products on display before wintertime. Those are all constant wattage cables, surprisingly. The difference with those is that they're about 5 watts a foot. They usually fluctuate between 5 to 6 watts a foot, and they are very inexpensively made. And I'm going to give you a little tip on these real quick, is that, you know, if you want to have a cable where your cost per foot on that cable is down around 50 cents, which is what those are, so that you can sell them at retail for $1 a foot, the jacketing is often made with PVC. And one of the byproducts of heating that PVC up to a pretty good temp is a chlorine, which takes the form mostly of a gas inside of the jacketing of that cable. And it becomes highly corrosive to actually the bus wire within the cable. So what happens is these cables will actually destroy themselves from the inside out over time. So, you know, please, you know, if there's one thing I you know, take away from this webinar is, don't use residential grade do-it-yourself or heat cables for a commercial building application. They don't have the wattage output really needed to melt serious, you know, conditions outside, and they're just not going to have the life expectancy that you're going to be looking for that you would get out of a commercial product. So just want to clarify that. So you know, another thing with these constant wattage cables, just getting back to this here, is that they are very good for sidewalk snow melting, pipe freeze protection applications. So again, you know, really when it comes down to it, it's about figuring out what's the best cable to use for this particular application that we're doing. And when we look at this cable's cross section here, you know, very simple as well, just 2 bus wires. And the resistance wire is the one to really kind of pay attention to on this slide. That resistance wire, you can see how it's spiral wrapped around both of the buses, and that's what's creating the resistance or heat output on this particular cable. The tighter you have those windings, the higher your wattage output per foot is. And the further apart they're spaced, the lower it gets. So not very complicated as far as how they design and manufacture these cables. What I do think is interesting is that that's a 37 gauge nichrome wire that can handle 480 volt. So when you think about 37 gauge in terms of its thickness, that's thinner than dental floss. And that stuff can actually take 480 volt current for 15 to 20 years and still survive. So I do find that part pretty interesting. And then we've got mineral insulated cables. Okay, some of you folks might be familiar with these, especially the electrical folks. Mineral insulated cable comes in 2 forms. One is a power cable, one is a heat cable. We see the power cable side of it when we're doing things like fire pump protection, so that, you know, to ensure that, again, the fire pump can continue working in fire rated conditions at 1,000 degrees. They're built very similar, only one has a resistance wire in it and one does not. So we have the one with the resistance wire that creates heat. The best way that I can describe an MI cable is that it's very similar to like an electric element used in your oven. Like if you have an electric oven, you see that that element in the bottom of the oven that's twisted into, all kinds of funky shapes. The outer jacketing of an MI cable is either going to be copper or stainless steel. And we tend to go with copper when and if we can, because it's much more malleable than the stainless steel is, and it's also less costly per foot. This is a great permanent type of solution cable. We use them predominantly to embed them in concrete for sidewalk snow melting applications, but they work wonderfully well too in roof and gutter applications, especially with some of these older historic buildings that have like slate and copper roofs. We can actually get that copper on the jacketing of the cable to variegate or kind of turn green, that same oxidation process that you'll see on copper flashings and copper gutters on some of these historic type buildings. The nice thing about this cable is it's extremely resilient. This is a product that could last 30 plus years. The big downside to this cable is that, again, it behaves like a constant wattage cable. You cannot let it touch against itself or it will burn through. The other part is that this is not a field serviceable cable. So the measurements have to be exact. These products are actually built to length. So depending on what the application is, how much heat output we need, this product will be engineered and built to a specific purpose. Again, that can kind of put it into another advantage category, which is this cable, because it is a fully welded metal sheath on the outer part of it. These get hydrostatically dunk tested for their UL rating, and they can't leave the factory until they've survived at least 24 hours in a submersible dunk tank. So these products can really be used to be submerged underwater for long periods of time without any fear of having water ingress and shorting the cable out. So we've had some very creative experiences with these particular cables and used them to de-ice sump pits. We've used them to de-ice airplane hangar doors, or we'll put them right alongside the steel track on those huge, sectional panel doors that fold across an airplane hangar. So again, great resiliency, higher on the cost side of things. Definitely not something that you can just splice an extra 20 feet onto out in the field. So again, very application specific. And when we look at, the cross section of this particular product, it is constructed or produced almost exactly like an electric industrial heating element would. Most of the time in the electrical elements, though, however, you'll just have, again, the same type of solid conductor through the middle of it with a resistance wire wrapped around it. So again, moving on, we're going to look at the self-regulating polymers. This is a product that's it really, I don't think has really hit the mainstream, we could say, at this point, but it has been around for 15 to 20 years. And we started getting into this product because it was able to be powered through a low voltage system. DC power, low voltage transformers are how we get power to these particular heating elements. And the self-regulating polymer works exactly like we talked about with the self-regulating cable, is that it works off expansion and contraction based on the surface temperature of what it is up against. So the nice thing about these is that they're incredibly thin. They come in widths from 3 inches up to 12 inches maximum. And one of the really nice features is during the installation process, you can use a non-grounding fastener. Okay, so anything galvanized, like a galvanized staple, nail, screw, and you can drive it right through this heating element and it will still continue to work. So it doesn't have quite the vulnerabilities that some of the other cables do during the installation process. It is something that can be used, for both roof and gutter and for sidewalk snow melting application. But we're going to get into some of its advantages and disadvantages a little bit further down the road. So again, talking about this, we did talk about the expansion and contraction and how these things basically work. But again, in most cases, we're seeing these embedded more in concrete than we are underneath the roof. And when we talk about its little cousin here, the brass tin conductive mesh, it's a very similar type of heating system. Both of these use low voltage DC transformers to apply power to the heating element. So essentially, where I'm going with this is that for the electrical folks, again, they've got a little advantage here. Is say photovoltaic systems like a solar system or a wind turbine on your property. Those are creating DC power, and then that DC power goes through what's called an AC inverter, gets converted over to AC power so that you can use it, let's say, in your 120 volt outlets, around your house or your building. The nice advantage to these particular systems is that you can run that DC power straight into these heating elements without having to go through an AC inverter, which is often, pretty big dollar piece of equipment when you're doing renewable energy conversion. So it does make it pretty convenient to be able to go straight from your solar collectors, let's say, right to a heating element and apply it directly to your needs. So, that part of it's pretty slick. The difference between this metal conductive mesh, versus something like the self-regulating polymer is just in the material itself. They both essentially do the same thing. The homogeneous polymer gives you the ability to self-regulate, whereas the tin copper mesh does not. The big thing with these is that when you terminate either of these products, the self-reg polymer or the conductive mesh, you do have to take very good care on the termination plates that adhere to these products. There can't be any, loose ends, loose connections, or hairs, let's just say hair-like strands hanging off of these things, because they can get very hot, like hot to the point of ignition. So, this is something that we look at as being a bit more into the future for roof and gutter de-icing. Once we can get a bit more of an established, let's say, installer base that's very well versed in proper procedure as far as making sure that can't happen. The difference between these and, say, a line voltage self-reg or constant wattage cable is per code. On the heating cables, on the self-reg and the constant wattage, you have to be on a GFI rated circuit. You have to be able to have ground fault interrupt to help take that cable out if there's an issue that it incurs. With low voltage, that's not a requirement. So if something kind of goes wrong with a low voltage system, that you don't have that backup to cut the circuit. So, with these, proper installation is really key. So again, this product is used predominantly more for, I would say, radiant floor warming and sidewalk snow melting versus, say, roof and gutter de-icing, because again, the product just hasn't been out there so long to where you've just got this, massive install base that's qualified and that's really good at what they're doing. So a nice appeal to these is that, again, either of these systems, you can actually turn up or lower the intensity based on how many transformers you have wired in. So if you are after energy efficiency, let's say if at first you wanted fast performance melting, we can size a particular system to give you that fast melting pace. And if down the road you say, hey, I want to switch that from fast reaction to energy savings, where now we just hold, say, a slab temperature for months, and become much more energy efficient there, you can actually remove transformers out of the system and then just reduce it that way. Okay, so that kind of wraps up a little bit of familiarity with some of the heating elements. So now we're going to get into the applications themselves. And I want to stick for a second on this particular slide because I think the picture says a couple of things here. One, when we talk about roof and gutter de-icing, is that some folks have an idea in their head that it's supposed to make your roof entirely bare or void of snow, which is not the case, okay? So I know that this picture kind of depicts that. And there's a couple of reasons. One, it was a pretty light snowfall. If you can tell by the neighboring building over there, not much fell. The second thing is that these cables are basically on a tin flashing, which is helping to transfer and conduct that heat a little bit better across a wider surface area. But three, probably the most important, is that is definitely a high quality install right there. I mean, whoever put these cables and clips up, that's how you do it, folks. That's a really, really neat install. And just to reinforce that, really the heating cables are there to help path water off of your roof before you have a chance for them to turn into puddles and then the ingress and all the fun starts. So again, very safe and reliable way to help prevent leaks. I mean, this is, technology that's kind of been around for decades now. And again, nothing against the be on this call that are architects. Generally the architects want to design buildings that have great architectural features that can include dormers, gables, skylights, which are great. The thing is that when a snowstorm comes over and dumps 6 inches or 1.5 feet, or go out to Buffalo and you get 4 feet, we can't oftentimes predict, exactly where's that snowfall going to go on the roof. And then, of course, how much sunlight do you have coming over the building that's really going to help melt that snow off, okay? I mean, ultimately, let me preface this application with the fact that you still need Mother Nature to help you melt snow off the roof. The heating cables are there to kind of help in those instances where, again, you're getting lower sunlight, places where, again, as the sun's traveling over the top of that building, you may only have 2 hours of sunlight in this valley, and you're just getting a melt and refreeze that continually happens until damage is done. So again, thinking about this more in terms of the fact that it's really there as an insurance policy to a very expensive roofing system that building owner just paid for or may have just redone on their building. So again, these kind of help protect your primary investment. That's really what it's there to do. So when we look at residential grade, generally 5 to 6 watts a foot on the cable is acceptable, and that works for most residential applications. If we're going to go commercial, we really recommend being a bit more around 8 watts a foot, especially if you're somewhere here in the Northeast that gets any sort of significant snow load. If you're down in, say Mid-Atlantics where you're really not seeing much snow accumulation, you could get away with a little lower than that. But up here, if you want to be able to sleep at night, not have to worry about any icicles, we want to be at least 8 watts a foot. So when we look at that commercial grade application, again, self-regulating cable is going to be the dominant cable choice in this application. And the nice thing about these is that, again, you can cut them into field. We just have to have a real good idea layout wise to how many feet we're going to get per circuit on these. The mineral insulated cables are actually pretty popular too with roof and gutter because of the fact that we get to engineer the wattage output of that cable. So again, we can design an MI cable to put out exactly 8 watts a foot, or somewhere between say 8 and 9 watts a foot, which could be totally safe and fine on a slate and copper roof. Now, if we're going to use that same type of cable, but we're going to put it on an EPDM roof, we might want to get that thing down around 7 watts a foot, just to ensure that we don't have as much, we don't have enough heat output to where we would have to worry about it embedding itself in the surface of the roof. So, again, MI cable it's a very durable product. It's not the easiest to work with, but generally once you put that cable up on a roof, it's pretty much one and done. The semiconductive polymers and the conductive mesh, what's really neat about those in the roof and gutter application is that they actually go underneath your shingles. So it's a hidden system. You don't see anything from the outside, which is really nice. But realistically, it makes it kind of a tough install because your roofing guys are going to be hinging on the installation of that particular system. And you don't want those polymers or those conductive mesh products being left exposed to direct rainfall or the elements. So generally you have to have the roofer and the electrician in perfect concert with each other to pull those jobs off for roof and gutter to be much more efficient. So when we look at a graphic that helps depict how and why this dilemma happens on buildings, is that, we see how warmth, and interior building heat can move up through, and especially these older buildings that have subpar insulation or a roofing material, is that the inside climate is going to help exacerbate the melt on the roof. So what typically happens is that obviously the melt, the melt is coming down the roof at its angled pitch. And then when you get to where this outer wall and the roof meet, you've suddenly moved from basically what was helping to keep it heated from the inside on that water on the roof to now you're hitting a completely cold ambient temperature overhang. And that's generally where that water begins to refreeze until it continually piles up to make an obstruction there. You get water pooling, and before you know it, the leaks are coming in. So the greatest point of loss is where the outer wall and the overhang meet, and that determines generally how the design is going to go from there. If we're looking at a building that's got an overhang of say 2 feet, we want to be at least 1 foot above that overhang length when we're running our cables to make sure we can pick up the water on the warm side of the building and path it through the cold section successfully into the gutter, down the downspout and away from the building. So when we look at that sawtoothing effect, okay, I know it's kind of a corny word, but you'll see those zigzag patterns across the bottom eave or whatever, the overhang of a roof, and we call that sawtoothing. And when you sawtooth across, say, an asphalt shingle roof, you want your bottom points to be about 2 feet apart from each other. And the reason for that is that if you go wider than 2 feet, you want to get into 3 feet or 4 feet, there's enough surface area there to still accumulate a good sized chunk of ice and create a nice sized icicle. So by keeping it at 2 feet, you're never going to get enough significant buildup to create a hazard there. Obviously, if you try and hem it in closer than 2 feet, you're going to use a lot more cable to melt that roof off. So again, unless you're in a very high snowfall area or someplace where, again, you have to keep it off of a particular area, 2 feet's the magic number. That's the right number. And we want to go up the roof, vertically up the roof, at least 1 foot past where the outer wall and the overhang meet. Okay, so that's how we determine what the distance is on those triangular points. So when we talk about things like, skylights, gables, dormers, again, obstructions where that can block sunlight access, we kind of play those by ear, right? It's to get an idea of how much natural light is getting over the building to look at those particular applications, but we may bring in our spacing, or widen it accordingly, depending on what kind of severity you've got up there. So again, it kind of brings up a good point with roof and gutter application, is that it's not that you necessarily have to do the whole thing. Again, you can just do certain areas of the roof that are problem prone, and if not, at least with new building spec and design, let's put it to you this way, is that I would strongly recommend that if the building owner doesn't see the value in putting a de-icing system on the roof initially, you may want to at least recommend or prescribe having enough electrical up near the roof, electrical provisions, so that if and when a system has to get added down the road, it's easy to get to. It's easy to tap that power instead of trying to run power back up from the basement, things like that. So just a little spec tip there. So when we look at metal roofs, okay, a lot of graphics that you'll see on manufacturers' products show a cable going right up alongside of that vertical rib and coming right back down the other side. That's really hard to do out in the field. That cable is not very flexible. And generally what we do is we just sawtooth right between those metal ribs on the roof. It just makes the installation incredibly easier, much less time consuming, and even more effective. So one of the things too that, this last bullet point that's a nice design tip is when we talk about doing layouts for roof and gutter, we have to do both the downspouts and the gutters as well, right? Because once we get that water moving off the roof, we have to continue moving it down the gutter and downspout and away from the building, as in most cases, those are aluminum products. So not only can aluminum conduct heat, it can certainly conduct cold. So it is essential that gutters and downspouts get done just as much as anything on the roof would be. And generally when we look at the dollars and cents of what it is to either continue on a cable run, let's say by going down and up a gutter, and I know that's not easy without seeing some kind of a visual here, versus putting in a splice kit, good self-regulating cable splice is going to take a half hour to 40 minutes. So when you think about what the labor time is versus, hey, what's the extra 12 feet of cable going to cost me to just go down and back up again, more often than not, it's less money for you to just get the additional cable and keep the job rolling versus taking the chances on ensuring that installer is going to make a quality splice. One of the things that we'd strongly recommend, and we can cover that again during the installation segment, is that, take voltage readings before and after your splices to ensure that it was done correctly. All right, so here's a nice graphic that kind of depicts a little bit more what we're talking about, where the greatest point of heat loss is and where the freezing generally occurs on most of these roofs. Excuse me. And then the second picture gives us a really nice illustration of those sawtoothing points where we're looking at 2 feet on center. And if you can look at it, it's symmetrical. You guessed it. Those upper points are also two feet away from each other as well. So that's what kind of gives it that nice symmetrical look. Now, if you look on that right picture and you see how the cable itself has a little drip loop down into the gutter, very strongly recommended. It doesn't have to be completely pointing downward and perfectly tacked on both sides. As long as we get that heat cable about an inch or two over the edge of the roof so that water can follow the cable, drip down into the center of the gutter, and then get pathed off the roof, that's really ideal. I mean, so essentially what you really want is to have those tips of those cables hanging over into the gutter. All right, so the general rule of thumb with gutters and downspouts is that standard residential gutter is 4 inches wide, and you'll see 4 inches on many light commercial applications too. Think of it like this: you need one pass per 4 inches of width. A brand new heat cable is going to melt about 2 inches per side of it when you lay it flat on a surface. Okay, it's going to emit heat out to about 2 inches on each side of that. So again, on a 4-inch gutter, if you run a heat cable right down the center of it, you've got 2 inches per side, and you've got the whole bottom of that gutter surface area pretty well covered at that point. So as you can imagine, when you put one heating run cable in an 8-inch wide gutter, the heat's not getting all the way out to each edge of that thing. So basically, you'll be melting nicely in the middle, but you're going to gang up some ice around the edges where you're not getting heat to. So, basically that's the whole premise behind this is it's literally how far or how wide each of these has a melt path. Now, remember we talked about self-regulating cables in the very beginning about how they have a life expectancy. So over time, you're going to notice that melt path get a little bit thinner, a little bit thinner, a little bit thinner, till eventually maybe you've got 10 years on that cable and you're only getting an inch per side of that cable melting. So those are some of those indices that'll tell you, hey, look, it's probably getting close to swapping out cables here or something, or I know I'm losing a little bit of power on these things or a little heat output. So again, 4-inch rule of thumb. Same thing goes with the gutter or the downspouts as well. Is that the downspouts are typically going to be 4 inches in most resi applications. You bump up into commercial, they start turning into 6s and 8s, depending on the roof itself. So in those cases, yes, we're going to want to have 2 runs in the gutters, 2 runs in the downspouts. So every 4 inches, okay? And one of the things too that we do, because you can see on this graphic or on this picture, in the upper picture, they're actually using EPDM material to hold the cables flat against the gutter trough there. And on the bottom picture, we're using clips, metal clips. Now, some of you might be asking that question right now, when you go to put these clips on the roof, are you driving a screw through those? No. The last thing we want to do is create more leaks where we're trying to prevent them. So we don't advise, plunging a screw into anything on the roof. We typically use epoxy. This is a very high strength epoxy that ultimately takes about 23 to 28 days for it to fully cure. But how the process typically works is, the installer would go up there, mount his clips on day 1, and after about 1 day's worth of drying, there's enough tensile strength there to where he can go up and run the cable, let's say, finish that job. And it takes about, close to 3 weeks for that epoxy to fully cure. All right, when we look at downspouts, this one's interesting because I think we've all seen this before, is that some downspouts drain to the surface. They basically, just kick right out on an elbow, and they'll just basically pour water all over the parking lot or all over, the lawn or something like that. And then you got the ones that go underground into a catch basin. So when we're running the cable down a downspout, again, as we talked about, it's often a lot less expensive and easier to just go down and up the cable or down and up the gutter. Try that again, down and up the downspout versus doing the splice, okay? So if we've got the open downspout, like you see down there, gushing a little water in the bottom picture, we just want to come out of the bottom of that thing with a little drip loop, okay? Not enough to where the cable's hanging out of the bottom and people want to go down there and play with it, or, a landscaper can clip it with a lawnmower, but just enough to form a little bit of a drip loop down there. And then where we have the catch basin scenario, you can't see the cable going underground. So, it's going to sound really professional, but basically you just, you stuff the cable down as far as it'll go. So, essentially, you know, if you can get down to 2 feet underground, fantastic. You know, there's all kinds of obstructions that can be down there. You just try to get the cable pulled down kind of that 2 to 3 feet underground mark if possible. That gets you down to the frost line. But one of the things that I usually give installers a tip on is that they can drill a small hole in the downspout on the back side of it, so that if by some chance your cable didn't get down far enough and you begin to freeze and that water wants to work its way back up again, you've got a weep hole to exit some water out before it pressurizes and goes all the way back up to your roof. So the low voltage systems, you know, as we talked about before, these ones go on with the roofing material itself. So this is a bit more of a, you know, probably a time-consuming type of install when you're trying to coordinate the roofer and your installer of this particular product. So these products are getting cut to length. They have to be terminated to length. All the wiring is going to be underneath the roofing material itself. The nice thing about it, though, is that, again, that finished look is pretty slick. You don't see anything on the outside of the building. It just melts from underneath. And, you know, the one thing about the self-regulating low-voltage polymer that I apologize I didn't mention when we talked about its product description is that a big reason why that product was incepted to be low voltage versus, you know, our typical 120 voltages and above on the AC side is that by keeping it a low voltage product, it never incurs the degradation process. Remember, we've talked about that about 3 times now, is that, you know, these self-regulating low temp self-reg cables that run between 120 and 277 volts, those will degrade over time. This particular product runs between 30 and 80 volts DC. The magic number is 100. Once you cross the 100 volt threshold, that degradation process begins taking effect due to heat. If you stay below that, then that product should last indefinitely. So it is pretty compelling, you know, but again, it's a much more challenging installation for roof and gutter. Now, this is a cool product too, real quick, is the snow melt channels and trim. So these things are basically fabricated trim pieces that you can slide a self-regulating cable into that offer a really nice clean look, and they do a great job melting because you've got the conductive, you know, metal of that channel to help spread your heat across a wider area. You know, they work great until you see the price is really what it comes down to. So one picture that I want to just show you real quick is all the way to the right side where you see that 2-foot snow dump on top of those channels where you get that iglooing effect. So that's exactly what happens when you get a large snowfall. Okay, heat cable can only put out so much heat. So when you bury it in 2 feet of snow on top of it, the snow becomes an insulator. And now that heat becomes trapped. So it will basically melt itself into a nice little igloo or ice cave. Okay, and we need Mother Nature to come out. We need the sunlight to come out to help melt this mass down from above. You're doing everything you can from underneath it, and it will continue to help keep water from pooling on the roof, but you're just not going to see the gains from ground level when you're looking at it saying, why do I have 2 feet of snow on my roof? Well, you know, again, we have to give this thing time for it to catch up. Eventually the sunlight will come over the top of that thing, melt it down enough to where the ice cave collapses onto the cable. The cable will melt that, clear the rest of the snow off, and you know, everything's successful. Excuse me. So talking about controls, several different types of controls, and I'm going to pick up the pace a little bit here as our time is clipping along. So we do everything from single circuit controls, you know, which are very simple for, hey, I just need to put 50 to 150 feet of cable up and just handle a trouble area. There's no sense in many cases of having to worry about advanced controls to do something like that. So single circuit controls from multiple different manufacturers out there. Most of these are going to be set up to handle either 30 or 40 amps. So again, you can just come out of a breaker panel with a, you know, single 30 amp 2-pole. And this is basically your switching mechanism. So this control is going to have typically two different types of sensors on it. One's going to sense temperature, one's going to sense moisture. And then 2 criteria have to be met for that system to engage. So generally it's 40 degrees or below, and there must be moisture present on the sensor, and the system will automatically flip itself on. And this is done to keep the system from, again, burning needless kW if it was, say, 0 degrees out and no precipitation, or it's 45 degrees out and there's no threat of it freezing. Okay, so Most of these manufacturers, their controls are going to be very similar in terms of default settings and what they're really looking for between moisture and temp. You can get these things also in a GFI rated version or a non-GFI rating. Again, it's price pointing. So, you know, what is nice about these is that they act as J boxes. You can literally bring power into one side of this box. You can come right out of it with your heat cable run. And then as you can see from the, you know, the graphics here, those are the sensors that you would just place accordingly in the best location for them to get hit with snow. Contactor relay panels. This is a very popular system when we're talking about commercial and industrial applications because, you know, typically we're looking at, say, more than 2 circuits. You know, would be anywhere from 4 circuits, 8 circuits, who knows. Contactor relay panels are very simple, okay? We have to bring over each 30 amp breaker from a distribution panel to each one of those circuits on the contactor relay panel. So it does make it a little bit more labor intensive, but very simple as far as its electric operation goes. Essentially, you know, again, you've got a contactor relay panel. Let's say it's got 4 circuits on it, you know, sitting on the wall, and then your sensors are out on the roof looking for moisture and temperature. When they've detected both, it sends a signal back to that controller. The controller, you know, will read on its text display sensor wet, temperature is X, and system on, and it'll just automatically kick that system on. We can put timers into these as well, so that after the sensor has cleared itself, you know, after the water's evaporated off the surface of the sensor, it can continue to stay engaged for, you know, anywhere from a half hour up to, you can literally put it into a 24-hour loop schedule. So, so again, very, very logical, very simple in terms of their functionality. And we like the fact that a lot of these manufacturers actually don't give you too many options that you can play around with and kind of screw it up. So if you want to do that, you want to move into one of these larger breaker integrated panels. These ones are the ones that have all the options and come, as just mentioned, integrated fully with breakers. So these panels are, yes, they're the most expensive, but they're also the easiest to install. So instead of having to bring over, say, 4, 8, or 12 different circuits, you know, to a contactor relay panel where each of those has to get wired over, this panel distributes everything. So you would just bring in, say, a 100 amp or a 200 amp feed and make one power connection onto this panel, and then it does everything from there. So again, higher upfront cost, much more technology. I mean, these things will tell you where your faults are. These things have BMS integration. You know, again, you can have it send alarm signals out to phones, to, you know, pretty much everything you want to have it do, but again, it's reflected in the price. So the low voltage systems, these things, these low voltage transformers basically convert line voltage, either 120, you know, 208 to 277, and even up to 480. But basically they're taking that AC power and converting it and knocking it down to a low voltage signal between 30 and 80 VDC. So depending on what the application is for the low voltage system, you know, again, oops, I didn't mean to do that. You know, again, you know, the nice thing about them is that they get you away from the GFI code requirement, you know, but the transformers themselves, they do take some wear and tear. And that is probably, of anything within that system, the Achilles heel is a bit more to the transformer side of it, especially when you're pushing something like 480 in on one side and you're trying to get 24 out on the other. You know, depending on their usage, you may have to replace transformers every 4 to 5 years. So, so to get into the sidewalk, pavement, paver snow melting section, you know, what's really neat about this is I think the heat delivery is incredibly consistent versus a hydronic system. When we heat water glycol, we're pushing it out, you know, and where it's hitting, say, the sidewalk at 120 degrees or 140 degrees when it comes out, by the time that glycol's gone through its path or through its zone, you know, it's coming back into the boiler at maybe 70 degrees, you know, 80, 70, who knows, 60. Now, it's great for the condensing effect on the boiler itself, and it increases its efficiency greatly. But what typically tends to happen is that you're melting great when you're coming out, and then by the time you're hitting the end of that run, you're getting slush, because again, you've lost BTUs every inch of the way. The electric systems are very consistent, start to finish. So they're very, very consistent in their melt. And the electric systems have just far fewer moving parts. I mean, that is a huge comparison between the two, is the fact the electric system really requires next to no maintenance over time. Another thing that I really like about the electric systems is that to figure out how much your operation cost is per hour, the math is very easy. Essentially, when we spec jobs across upstate New York here, we're typically modeling them around 50 watts a square foot, which is, the same as hydronic is doing at 150 BTUs. It's roughly about the same amount of heat. The nice thing is on that electric side, though, is that if we, basically compute out that the sidewalk is 25 kW worth of heat, and if you're paying 10 cents a kWh, I mean, it becomes real easy to kind of do your math in dollars and cents as to how much the system is going to cost to run you versus, again, a hydronic system that's got both electrical usage and you're using fossil fuel as well. So, a couple of stark differences between these two systems. And then of course the electric system can operate far fewer hours versus the hydronic system because we don't need to continually cycle glycol and keep it moving. Many times these electric systems just come on or off as needed. And because they ramp up their temperature so quickly, generally we can heat the sidewalk, melt it, run the timer until it actually dries the pavement, and then the system will shut itself off. So yeah, typically here in upstate New York, if we're speccing at around 50 watts a square foot, that's good enough to keep up with 2 inches per hour falling. So that's pretty good pace. And, we can get down around even 40 watts a square foot just to pick up a little energy savings, but you're going to be a little bit more down towards that inch to inch and a half per hour as far as the melt rate goes. And then, of course, the most energy efficient, if you can believe it, is to just maintain a slab temperature throughout the entire winter itself. So if you literally just put your sidewalk on at 33 or 34 degrees from November until April, you won't be able to melt down a foot very quickly, that's for sure. It's going to take some time for that system to catch up and melt down a more sizable snowfall, but it actually uses considerably less, like up to 65% less energy to just maintain a slab temperature throughout the entire winter versus doing it on demand. So big thing with these immersion systems, generally these are going to be constant wattage cables. As you can see the picture in the bottom right there, they're using a snow melt cable mat, type of product there. And those come pre-serpentined in that product, which is great. You don't have to worry as much about that cable spacing or cables touching against themselves. You just want to make sure that, each of those runs is separated by about 4 to 6 inches, so that you're getting nice even heat distribution across the footprint. But as you can see, the time that it takes to put down one of these things is probably considerably less than, even the hydronic systems that are using the dimple plates and then just running PEX through them. And like the hydronic systems, if you were just reading the text on that slide, we don't cross expansion joints. We'll do anything we can to avoid trying to cross an expansion joint because you can never predict what the level of heat is going to be. So, typically what you're doing is you're just putting your wiring leads to one side of the sidewalk. And then what we want to do is extend those leads all the way back into the building or wherever the power source is going to be. We do not want to make splices out in the field with this particular product. We've seen it happen for years where, again, an electrician or an installer can talk as much as they want about how well watertight fittings might work underground, watertight wire nuts, things like that. We've seen them burn up. I mean, it's just, again, I think you're asking for trouble if you're making terminations in a quasite box underground. If you have to, at least make sure that the junction box or where you're going to make any of your wiring terminations is well above grade and does not have a chance of getting saturated. I mean, that's really the big thing, is just keep the moisture out of the connection. So, typically, when we're looking at this particular application as far as wattage goes, with these prefabricated kits, these cables are typically 9 to 12 watts a foot, and they're tightened up in terms of their serpentine or closeness to each other. If we're using something like a mineral insulated cable that we would bend the radius ourselves as we're putting that into the, into the sidewalk, let's say, those are being spaced about every 6 inches apart. And the cable itself is spec'd more around 25 watts a foot. So when we turn it on a 6-inch radius bend, we're getting effectively our 50 watts per square foot. Okay. Again, nice thing about these products is that if they're installed correctly, probably a good 20+ year life expectancy out of them. So again, better manufacturers, you're going to see higher warranties. You know, and again, we're going to talk real quick too about some of the tips on the installation side as we're starting to draw this thing down some here time-wise. So, you know, MI cables really have a nice permanence to them, and they work really well for curved radius bends or places where you've got, you know, non-square shapes. Let's put it that way. If it's square or rectangle, mats can usually conform to it pretty easily. Things like steps, you know, we can certainly snow melt steps. MI cable is a much better product for doing step systems versus the mats. The mats tend to buckle a little bit under the weight of the concrete, and it's not that it's going to impair them physically as much as it is we just don't want the weight to change the position of the cable to where now the cable might touch against each other inside of the pour, or, you know, wind up on the riser section of a step, let's say, instead of on the step itself. So that's why we usually suggest, say, something like MI cable for steps. The low voltage systems, again, you know, you can play with the amount of transformers used on these to increase your wattage output or decrease it. So once the material is down, it really comes down more to how many transformers do I want to use to supply power to that system, and that's essentially going to give me my pace of melt. Okay, portable snow melt mats, these are available too. This is something that makes it quick and easy for somebody that unfortunately missed that opportunity to embed a system into their concrete. You know, you can still kind of have your cake and eat it too. You can just get a mat system that fits on top of finished concrete that comes with a GFI cord set. And in most cases, yep, you're going to probably need the help of an electrician to bring a 208 or 240 volt receptacle outside for you to plug into, at least if you want to use the larger mats or daisy chain multiple mats together. But this is certainly a nice, you know, non-slip type of product that, again, can be used in about any application. All right, so as far as these layout tips are concerned, you know, the biggest thing is again, we can't let these cables touch against themselves or they will burn through. So your spacing is almost always going to be 2 to 3 inches. You know, when you get towards the edge of sidewalks or near expansion joint breaks, things like that, 2.5 to 3 inches is almost like what we were talking about with the gutters, those having, say, 2 inches of heat spread coming off the cable itself. One other thing too is when you have an embedded sensor in the sidewalk is that you do not want to get that heat cable like right up against the metal can that sensor is sitting in, or else you're going to get false reads. You know, kind of makes obvious sense, doesn't it? You know, but something that for specifiers, definitely something that, you know, we would want to have either put on that spec or brought to the installer's attention, because it's happened. And, you know, it's one of those things where you don't want to have to go back and correct these issues after the installation for obvious reasons. When we look at how these products fit within different types of pavement material, you know, you can see where we've got, you know, 2-part pour, you know, applications here. We can do them with pavers. You know, again, the big thing with pavers or putting anything like that above it is that you must have at least 1 inch of sand or stone dust covering those cables. So you cannot put the weight of those rocks on top of the cables themselves, or else you will break them. So again, they just need to be completely encased in some sort of sand or compactable media. All right, so this picture on the left is really a fantastic, I think that all this really just co-joins to show you exactly how simple these systems are. And if we go from right to left instead, you know, we go from like our main distribution panel to either a contactor relay panel or a single circuit controller on the bottom of the screen. And then, you know, again, you're going out to the actual pour itself. Okay, so that's it. I mean, there's really, you know, there's not much to it. You typically have, if we were to work it from, you know, the left back to the right, you know, maybe I've got a pavement sensor and an aerial sensor out there looking for temperature and moisture. And if it recognizes it, it's going to send a signal back to that controller. That controller sends its signal back to the contactor relay panel. which will close contacts, allow power to pass to the heating cables, and away you go. So, when you compare these systems again versus their hydronic counterparts, there's way fewer parts to them, generally a faster installation. For installers that are used to putting these things in, it's got to be night and day as far as the time it takes to actually integrate the systems. So in talking about the controls for these as well, very, very similar to what we just discussed with the roof and gutter de-icing, so I'm not going to spend a ton of time on it. So again, we're talking about single circuit controls and contactor relay panels, and then of course breaker integrated fully loaded panels that can pretty much do everything. So literally the same type of controls you're dealing with on the roof and gutter side. So we're just going to cover a little bit on installation best practices, and then we're going to get you out of here. There's only a couple more slides to this, so thank you all for staying with this. With installation tips, the first paragraph for any of the specifiers on this call, I can't reinforce it enough, is that, be specific. Anytime people are allowed to kind of take discretion out on a job site, they're usually going to use that to their advantage. So all things considered, this is really the part about teaming up with a good noteworthy or reputable rep to help you design these systems out so that you don't run into one of these installation pitfalls where somebody says I didn't know, or again I know that there's installers out here, some great installers that do a fantastic job putting these systems in. And, to them, kudos, because, really when it comes down to it, all it takes is reading the instruction manual the first couple times. And yeah, not to say that in the first 2 or 3 installs, there might not be a mistake or two, but you shouldn't be making mistakes after 2 or 3 of these systems. They're just too straightforward. The wiring is very, it's very simple, for lack of a better term. It's making sure you pay attention to a couple of details, which the biggest is measuring. Okay, if you don't damage one of these heating cables, whether you're putting up a roof and gutter system or embedded in concrete, just don't damage the cable. That's the biggest thing. If the cable goes in full structural integrity and it's not damaged, that's going to work for years, trouble-free. Okay, so that is the biggest thing, and the way that you check that is to measure it. And for those of you folks who are not familiar with a megger, it's in the upper right-hand corner there, that blue rectangle, the blue square. It works like a multimeter. You just basically put one probe on a bus wire, the other probe to ground, you push a button, and it tells you whether it's good or bad. I mean, this can give you a numeric readout. We actually have ones that will turn red, flash a red light if it's bad. Okay, so it makes it that obvious. So, the biggest thing is again, many times it's not the actual installing contractor that damaged the cable. It might be one of the other crews on site. The concrete guys, I mean, I like them, but they can be animals. I don't mean to say that in a disrespectful way, but these guys are used to plunging shovels and rakes and screeds and all kinds of things into that wet concrete. And if they hit one of those cables, yeah, there's a real good chance they could damage that jacketing enough to ground fault the system. So you're going to find that out the first day you start it up, and that breaker keeps tripping. So, typically I like to personally lie to the concrete guys, and I'll tell them that we run live voltage through the cables while they install. And that way they have a good, healthy scare, wondering whether or not they're going to get, burnt to a crisp for hitting a 480 volt wire, which of course I'll explain to them that, yeah, I'm lying. And I just like seeing the reaction. I think it's kind of funny on the job site, but if it kind of gets people's minds, into the fact that, yeah, just take care. Just don't walk on the cables. Don't drive a concrete buggy on them. Don't hit them with metal tools, and you should be fine. I mean, the big thing is just continually checking that cable with that megger tester before, during, and after the installation. And it also coincides directly with your warranty. So you're going to need to put in your megger readings and resistance readings at the end of the job to qualify for the product warranty, no matter who the manufacturer is. Okay, so it's a very, very important part, and probably the most important part of any of these installation tips. So, again, in summary, the electric systems, we think are involve far fewer parts in most cases, and they are generally a much easier installation. We love the fact that, again, especially with sidewalk systems, your energy costs are very predictable. We can figure out just based on how much power that system's gonna take as to how much it actually costs you per hour to run it. Again, the learning curve for installers it really should never go beyond 2 or 3 jobs as far as, being able to pull off a 100% clean installation with no issues. So really when it comes down to it, as we're making some of these changes, even the low voltage systems, in a world that's trying to electrify right now, could be a very compelling type of product, considering that it does have forgiveness on the installation side of it, and the fact that it can also take direct DC voltage from a photovoltaic. So that could be a great way of offsetting how much power draw, those immersion systems typically take, because that's usually our biggest disadvantage is, not many facilities have an extra 100 amps laying around. But thank you very much. I know we ran a little bit over here, and I really appreciate you sticking with us. I hope you all got something out of this. And as Ryan said before, if you feel like submitting questions, we're more than happy to help you folks in the future. And with that, I think we'll call it a day. Again, thank you so much and enjoy the rest of your week.